In the last video, we looked at rolling dice, say 5, 10, 20, 100, 1,000 times, which is a good setup for the illustration of what we call a sampling distribution. But basically what we could do is we could look at the process of rolling more and more times, and the idea of the law of large numbers is that the more times you roll the dice, the closer and closer the average of all the rolls will get towards the true average. But another question is, how many is enough? Is like rolling 20 dice enough, 100? But the idea is the accuracy will get better and better the farther and farther you go. And the short answer to that question is it depends on how accurate you want to be. You need a certain number of rolls to ensure a certain level of accuracy. And one thing that we could do is we could examine the pattern of rolling more and more times. So I've actually went ahead and created a histogram of rolling 5 dice 400 different times and seeing the sort of different types of answers you could get. When we rolled the dice 5 times, we got an average of 4.4. But notice that if I carried that out 400 different times, it appears as though getting an average between 3.5 and 3.8 was the most common result, happened about 90 plus times. Getting a 4.4 or somewhere in that general range, it only happened about 30 times. So it was much less likely outcome than your average. Rolling, say between a 3.1 and a 3.4 was fairly common as well. And what we can see is that, there's a distribution of average that we get when we roll dice 400 times. What you might also notice about this pattern is it's not exactly a normal distribution, but it does follow the general pattern behind a normal distribution, an important idea that we're going to look at. But let's say we rolled 10 dice 200 times and we did it more and more and more often. Notice that the types of answers we're going to get are actually way more concentrated towards the center. The average of 3.5 to 3.8 was the most common, 3 to 3.4 also relatively common. And the number of outliers, basically we had 0 outcomes that were higher than 4.6 and only 1 or 2 that were lower than 2.6. And as we know, the true average should be 3.5. The average of rolling a die is 3.5. And so, when we're rolling it 5 times, the most frequent result is 3.5, the true average. But we could get very, very low results because it's, there's always randomness. Like in Yahtzee, you have a chance to roll 5 sixes or almost all sixes. It's unlikely to happen, but very, very unlikely to happen. But it does happen from time to time. And the more and more you roll, the more and more you play the game, the more likely you are to see those sorts of crazy outcomes. But if you increase the number of dice, you're way less likely to get, let's say you roll 10 dice, very, very unlikely to get all sixes, right? Because each one has its own chance, and you could calculate those probabilities. The math that goes into those sort of calculations is what's called the binomial distribution. Actually, that is a chapter 14 of our book, but it's not part of our curriculum. So I'm not trying to get overly bogged down into this sort of probability math because it's not what we're focused on, but I think it illustrates a good point. And going back to the law of large numbers, the more and more we roll, the more the more likely we are to get a correct answer. Now, okay, so another difference is the difference between a population distribution and a sampling distribution. Basically, a population, this is kind of going back to the difference between a parameter and statistic. A population distribution refers to all of the individuals within the population, whereas a sampling distribution, this is kind of the key idea from chapter 15. Sorry, let me try to circle this because this is the key element to understand in our chapter. It describes how a statistic varies in many samples from the population. And these previous graphs are examples. Well, basically, if I take 10 if I have a sample size of 10 and I did this once, I could get an average of 3.5 or I could get an average of 3.8. When we took a sample size of 10, we got exactly 3.5 as our mean average of rolling 10 dice. But when we did a sample size of 20, we got 4.15, or, we could have gotten 3.0. We could have gotten 2.7. The mean varies as we take different samples. And what we refer to this as a sampling distribution. If we take lots and lots of different samples, we could view the pattern of the distribution, and because it describes how that statistic varies in many samples. Now, in general, usually when we're doing our own statistical survey, right, we're trying to study, let's again, going back to one of the examples I like to use. Let's say we have 2,500 students at Point Loma, and we're taking a sample of 100 of them. That is one sample. But again, say we took a different sample, we would get different results. And the results, if we kind of graph them and looked at those distributions, that's what we would call a sampling distribution. Now let's get into some of the keys of a sampling distribution. So let's go ahead and look up the mean and the standard deviation of a sample mean. And so it says, suppose that X bar is the mean of an SRS. Remember, this stands for simple random sample, which just, is the best type of sampling that we always want, meaning there's no bias. If we have a 2,500 PLNU students, every single student has an equal chance to be part of our survey. And we're not just taking data from one of our classes. We're taking, we could use again, like a random number generator to figure out a random selection of those people. But it says, suppose that X bar is the mean of a simple random sample of size n drawn from a population with mean mu. So again, it's kind of like, here's the mean we obtained from our data, and we're actually talking about its true mean mu with a standard deviation of sigma. Then the sampling distribution of X bar has a mean mu and a standard deviation of sigma divided by the square root of n. Now I'm going to go ahead and highlight this because this is a critical thing to remember from chapter 15. And it's the most misunderstood thing about sampling distributions. But essentially, the sampling distribution is a different distribution than the actual results. So it's sort of like, let's say that our college students were just studying their age. Let's say that the average age is 20 and the standard deviation is 1 year or whatever. If we take a sample, it's going to have its own mean and standard deviation, right? Which we would call X bar and S. However, the sampling distribution, that's something different, right? Because again, going back to the previous example, it's like if we took lots and lots of different samples, what would the variance, we could look at what the standard deviation mean would be of those. But if we look at the dice rolling example, notice that the average, again, kind of looking at this as a normal distribution, approximately, the average is the true average 3.5. The mean is the same as the mean of the sample. And notice for this sample, again, our mu, the mean of our actual normal distribution, is right there in the middle, 3.5, which is not, and remember, X bar stands for every individual sample, but each sample, there's a lot of different samples in a sampling distribution. But the thing that is critical about this is notice the standard deviation. The standard deviation of let's say we had a sample size of 5, it looks like it's going to be somewhere about, 0.9 or something. Remember, it's the distance between the mean and the inflection point for the data. It's kind of like where the data sorts to have that skew value. Again, you could calculate it if you actually had the data points, but notice comparing it to this one, notice that the standard deviation of this one appears to be somewhere more about right here, maybe like at 2.9 or something. I don't know, let's just say this is about 0.5. But the point I'm trying to illustrate here is that the curve is more dense. It's more packed towards the center when you take a larger sample size. Kind of my point was there were more extreme values when we took a smaller sample size because we only did 5 rolls. But when we did 10 rolls, it's a larger sample size. There were less extreme values and the data was more closely clustered towards the actual mean. Because that's what the law of large numbers said, right? Is that the larger the sample size, the more accurate it will be. Let's say we did it 100 times, it would be even way better than this. And that's what this is. Basically, what this is saying is that the standard deviation of a sampling distribution is smaller than the original sample by if you divide by the square root of the sample size. So like looking at that example, the mean value of rolling a dice was 3.5. We could also calculate the true standard deviation of that as well, which I've done, and we won't bother by doing that. But what it's saying is that it will get smaller and smaller by, let's just say that the standard deviation is 1 for rolling a dice. That's not what it actually is. Or let's say it's 2. And let's say our sample size was 5. If our sample size was 5, the standard deviation of the sampling distribution would be the actual standard deviation of the whole divided by the square root of the sample size n. So the square root of 5, this would give us approximately 0.9 or something like that. Again, I'm just sort of making up numbers to try to illustrate my point. And let's say we had a sample size of 10. let me erase this. We had a standard deviation of our actual population. Sorry, my pen is not working very well. Let's just say it was 2. And if we divide it by the square root of 10, that's approximately 3. This is going to be about 0.6. Again, I'm not actually doing math right here. Actually, you can't even see what I'm writing because my face is in the way. Sorry, poor planning on my part. But essentially, the standard deviation is smaller for a sampling distribution when it has a larger sample size. And the standard deviation is reduced by the square root of n, if you divide it by the square root of n, and it will get smaller and smaller. And this was illustrated in the graphs of those sample distributions that I showed you earlier, because basically the data is more closely packed together. So let me wrap this up. I feel like I'm rambling and losing track of my point. But essentially, in a sampling distribution, the sample size matters. The larger the sample size, the more likely it will be closer to the actual value. And this just means that the standard deviation is smaller because there is less variation when you have a larger sample.